Can't promise. Let's see.
Controlled entertainment. I mean, it makes sense that landing at night would be.
Yeah, landing at night.
I wonder why I had
Yeah.
takeoff at night.
My mother-in-law very sarcastically said when that came on the video, she said, "Oh, night landings, Lee's favorite thing." I'm like, I'm taking it that it's not his favorite thing, huh? Not so much.
I wonder why taking off at night though would be.
Yeah, I guess you take off, you take off. Like if you're launching yourself, you're launching yourself, I suppose.
I guess maybe it's because you can't see where the drop off from the ship to the ocean is.
Maybe. Oh, this doesn't see me. There you go. I know we're gonna have some like weird internet issues today too, because as you saw there, here we go, tearing up the whole neighborhood. Guys, don't do the weird pillow thing again. It's distracting and stuff. Just leave them where they are. Stick them in your lap, or if they're in your way, stick it on the floor. But don't pile them up and whack each other. Not cool. Yeah, really. Don't whack Caitlin. She doesn't want to get whacked up with the thing. All right, so it is connecting. It's a little slow. So anyway, that's just I thought I'd share it with you guys just because it's neat. It's not something you're probably going to get to see anywhere else. So I thought, I'll share it. It's fun. Yeah, the physics involved in that are crazy. And a lot of those guys, okay, then a lot of those guys went on to be commercial pilots and whatnot. And as you saw, the one dude went on to be an astronaut. And he's actually known a couple guys that have gone on to be astronauts. And Charlie Bolden, who used to be the NASA director, was a Naval Academy classmate of my father-in-law. So a lot of those guys, if anybody's interested in any of the academies, like Naval or Air Force, all of the services have academies, except I don't think Space Force has one yet, but maybe it will by the time you apply to college. But the academies are very, very challenging to get into. But I don't know why it's
Coast Guard Academy.
yeah.
Maybe they'll have an academy by the time there's actually threats out there in space.
Yeah, it could be. They probably will get ahead of it, though, I imagine.
Yeah, I would like to be ahead of them.
Yeah, I would think that that's where we would want to go. I don't know why this is giving me trouble now. It's fine all day long. But
That's
What?
come
I mean, like a
on.
laser.
Me. So anyway, a lot of them went on, like I said, to do
Be a Death Star.
other things involving my father-in-law went on to be a commercial pilot for many years. He first flew for it was Pan Am, and then it became US Airways. And he flew a smaller plane called a Dash 7. It's like it's got one of those wings over the top, and it's a commuter jet. So it's not like a long haul jet. It's short flights, short distances. Okay, I'm gonna turn this off and back on again because it was just being a real pain, and I don't know why.
America would be the country to have a Death Star.
Yeah, that would be about right.
Yeah, they have a Death Star and a bunch of Star Destroyers.
Oh, Russia.
So do you know how they know
That'd
on the deck? Do you know how those guys know how to land, like where to put their plane? So
Rocket.
have you heard? Yeah, do you know what the meatball is? Yeah. Can you explain it? Do you want to explain it?
So there's
There's a thing called a meatball. That's what they use.
yeah, that's what they call it. So there's this thing on the carrier, and it has 3 different levels, and it shoots radar beams in certain angles. Like I think it's the carrier, like the end of the carrier deck. They shoot it out this way, so when the planes come in and they're in whatever zone they're in, it shows them on their on a little screen what level they're supposed to be at, kind of, so that they can make the right approach angles, and that's why too low.
Yeah, it's got the way it works is it's got mirrors and refractory light within it. So you can tell if you're too high or too low because the light is there's like I think there's a yellow and a red or something, and then there's like a green. But what you're trying to do is physically get yourself in a position where you can see all of them at once instead of this one, that one, or whatever. It's like there's a point where you can see everything right. That's when you know you're lined up. That uses it to line them up. And apparently it's pretty effective because I don't know what the problem is here. It's gonna make me crazy. Let me give it just a minute. Thank y'all for being patient because it's being really stupid. It was fine all morning. I don't know if if we got spotty internet or whatever, but
You know her. She's dead.
yeah, yeah. Let me get this one going at least. Yeah, ding dong. I know. Stay participants. Audit. No audio. video. All right. So that one's functioning. Oop, 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 yay. Cross your fingers. See? Hey, hey. Where's my clicker? Over there. There you go. It's going. I think it's going. Cross your fingers.
He was like, but it's.
Hey, that only took 5 or 6 tries. I don't know what the problem was, but yeah. Oh, it's its favorite too. Okay. All right, we are there. It just took a while. I apologize for that. So I discovered something, and this is very strange, but apparently, my clicker that I got works great with PowerPoint, with Zoom on and everything. If you're going backwards, but if you put on Zoom and you put it up here, it will only go backwards. It will not go forward. It won't show you. It won't show you forward. I can't tell you why. So I still have to, yeah, I know. Welcome back. I still have to kind of stay over here. Okay, so we are on Igneous Rocks today. So thank you for the little delay. Thank you for being patient for the little delay. And I do have some handbacks for you. I have a lot of Ricos in here. I have some very good ones. Let's see. I had 2 to hand out because I had, who was it? Was it Piper? And then there's you. And then there was one other. Y'all remember who it was? Or do I need to look it up? Somebody else. Anybody remembers?
Wasn't me.
Was it? Oh, yeah, wasn't it you, Caitlin? I think, there you go. All right, and then this one was, no, this is Caitlin. All right, so Bailey, I'm gonna have you guys pass it around. Bailey. No, you do Bailey, please. Parker. Chloe. We have them. And Milo. That's okay, I saw it. And Piper and Kate. Okay. What did mommy say? What did mommy say? Piper and Caitlin. Okay. So, Igneous Rocks. We are talking Igneous Rocks today. Igneous Rocks formed from lava or magma. That's right. Okay, good. So yeah, above or underground, that is correct. So what we need to do today is we have a little review, I think, at the beginning here, but we get ourselves into igneous rocks pretty solidly. So more rock classification. All right. Somebody tell me what classification is. What does it mean to classify something, Piper?
To put something into groups of its characteristics.
There you go. Yeah. So to group things by whatever characteristics. So let's say I have an apple, a banana, a cherry, a tomato, and a carrot. What is one way I could classify apple, banana, cherry, tomato, carrot? James? Color. So I put what, maybe apple, cherry, and tomato together? And then, yeah, okay, what's another way?
Fruits and vegetables.
Fruits and vegetables, that's another way.
There would only be one vegetable.
That's true, technically, yeah. Milo?
Taste.
Taste, okay, sweet, sour, Bailey.
Their size, they're like brown.
Shape, yeah, that's another good one. Alex, give me one more.
pH.
pH, okay, that's a very specific way, but yes, that could be
Ooh, texture.
texture, yeah, so there's lots of ways, all right.
What
So
color it turns when it's burned?
there you go. So when we get into rock classification, there are multiple ways to classify rocks, like lots of ways. There, you can do color, you can do grain, you can do texture, you can do intrusive, extrusive, and then we have that whole Bowen's reaction series that you guys just saw and used a little of in lab, maybe, perhaps some of you did, I don't know. So color. Now, color is what determines the color of a mineral. So mineral color is determined by the what that make up its chemical composition. Bailey, you go.
Elements.
Yeah, the elements, that's exactly what we're looking for. So the elements that make up its chemical composition. That is what's going to determine the mineral color. Now remember, minerals make up rocks, so it can determine the rock color too. So you have minerals that make rocks, right? All right, so the other things, just so you know, is there a typo?
Finely spaces structures.
Oh, you're right, should say finely spaced. Woo, you caught one. All right, there's one for you guys. You guys are doing good. All right, so other factors, things like chemical impurities can change the color, physical defects in the structure, mechanical mixture of very fine impurities and also finely spaced structures in the mineral. So for example, quartz and then like milky quartz has gas in it, right? And that's why it doesn't look clear. So that's something like a physical defect maybe in the structure. I will put a link to this in your weekly email, but there is a podcast called Ologies. I know it's on Apple Podcasts. I don't know if anybody's ever listened to it, but they got like 200 episodes. And the host, what she does is she picks anything that ends in an ology, which is pretty much anything that can be studied, right? And she brings in an expert on that topic. And it just so happens that I happened upon one this week that was a gemologist. So this person's entire job is to, study gems, and that's for, value, for pricing, for jewelry, for insurance purposes, all that kind of stuff. And it was really, really interesting. Actually, you'd think it would be kind of boring, but she made it very interesting, this conversation about gemology. And apparently to get certified as a gemologist, there's only one place that does it, and you can do the class online or in person, and you got to go take this test. I think she said it was called 20, and there were like 20 things on the test, and they just kind of throw some things down in front of you and you have to identify them. If you get one thing wrong, you fail. So yeah, that's
Like take the test roll.
yeah, she apparently failed the first time and took it again and succeeded the second time. So anyway, it's really interesting. I'll send it to you, and there's a lot, you could listen to any of the ologies because they're all, I will say there's a little language. She does have a little language, but nothing you guys can't handle. So color, mineral composition of a rock determines its color. So the elements determine the chemical composition of a mineral that determines its color, and then the mineral composition determines a rock's color. So you got light colored, white, yellow. Those are usually mostly quartz, plagioclase, or calcite. And granite would be an example. Granite's usually full of lots of quartz. It's usually pretty high silica, like the one that Drew had. We were talking about it. I told him I thought it was pretty high silica because it was light colored. And then you got dark colored black rocks, and those can be made of things like pyroxene, biotite, or chromite. If you guys remember, the two mica samples that we had came from different boxes, and they were both, the biotite derivative of mica. So those were the darker ones. So all rocks are made of minerals, and depending on the number of minerals, they can be subdivided into different categories this way too. So here comes our wonderful Latin Greek root thing again. So you got monomineralic and polymineralic. What's mono mean? Ooh, Petra. One, right. And what's poly mean, Bailey? Multiple, many, more than one. So if you see that word and you're like, what the heck is monomineralic? Well, one mineral or multiple minerals. So if you hear a rock is polymineralic, it's probably like what most of you guys found. If you find something that's monomineralic, that's when you find like a pure mineral, right? So to find a rock that's monomineralic, it's like a big chunk of pure mineral. So if it will go, I'm telling you to go. There you go. All right, texture, there's another way. So we just said color, and color can help determine whether it's mono or polymineralic. So there's one way to categorize was color. Here is texture. So texture, what'd you find?
I have another way to identify.
Well, we'll get there. There's other ways, yeah.
Taste.
Oh, I wouldn't like
No.
Now, you could find a salt that way. It would be a salt, but yeah. Is this rose quartz or Himalayan salt? I don't know. Let me look at no. So what's a rock's texture? So that's how it feels, right? Obviously. And what's going to determine the texture are the grains. So do you have big grains, small grains? That will determine the texture. So the main things we're going to look at with grain are grain size, grain shape, and grain pattern. All right, so you're dealing with grain size. Here's an example of a coarse grained rock. That's granite. Coarse grains, big grains. Okay, so we'll get into what makes big grains versus little grains in a minute. But you can see all those separate grains, right? So that one is going to be a coarse grained rock, and it's got large grains. Last week we talked about large grain, fine grain, right? Now you can really see the different colors of grains in this rock. Now you've also got these fine grain ones. So this one in this case is dacite, and that's pretty fine grained. It looks almost like sandpaper or a sandstone kind of. And then lastly, when you get the ones that have no visible grain, so this is your obsidian here. Yep. So that has no visible grain. That's really glassy. So that's one way you can categorize by grain size. If you're going to categorize by grain shape, another example would be conglomerate. Now this is a sedimentary rock. And this is actually one of my absolute favorite kinds of rock because I think it's just funky. So conglomerate has these rounded grains in it, but they're like pebbles of other kinds of rock that are mashed together and then held together by some kind of mineral type of glue. And they're just really neat. Now, they're also called pudding stones. And I know it's weird because they don't look like pudding to me. But anyway, they're called pudding stones. And I have a good friend from college who actually lives on Lake Huron. Like there's a beach in her backyard and it looks like an ocean because Lake Huron's so huge. So tough life, but she's a doctor, so she's earned it. So anyway, you've got this this beach in Lake Huron and it washes up pudding stones and she collects them when they end up on her beach and she takes pictures of it and puts them on Facebook. I have to find one of her pictures for you guys. They're really pretty. And then another kind of large grain stone you're going to get here are these breccia. So breccia is really jagged. So you can see the rock segments that make up the breccia are pointy and, you know, they're probably less weathered than the rocks that make up the conglomerate, the smaller fragments of rock. So leave each other alone, crazy people. So here's something to note. Igneous rocks don't possess round or jagged grains. If you ever see a round or jagged grain rock, it's not an igneous rock. But these are both sedimentary, and that doesn't mean that sedimentary rocks can't be fine-grained or more coarse-grained, right? But an igneous rock cannot have large, round, or jagged grains. Okay, so when we get into grain pattern, good example of quartzite. Here it is. There's really not much of a pattern, right? They call it non-banded. There's another term for it too that we'll get to in a minute, but quartzite's a great example. It's metamorphic, and it's basically quartz that's starting to go through the metamorphic process, but it's not that beautiful clear quartz or the rocky quartz milky quartz that you would see if it was purely metamorphic. The other type that we deal with, we're talking about grain pattern, the main other type is banded. Does anybody know how to say the name of this kind of rock? What is it?
Nice.
It's nice. Yeah, just remember it's a really nice rock. I know it looks like goodness or something. Keep dropping things. That's terrible, but it's nice. So when you see GNEISS, just think it's a nice little rock. Nice. So that one is banded clearly, and it looks like it's banded by something that's a much more high silica form of metamorphic rock that's been through the whole weathering process, and then bordered by a darker one. So one that was a higher silica. I used to collect rocks when I was a kid, and I had one similar to that. It had a big white band like this in the middle, and then really dark on top and bottom. And I called it the Oreo rock because it looked exactly like a cross section of an Oreo. It was really cool. Those are neat. I like them when you see them. You can find these very often, like when people get gravel dumped on their driveway or whatever. These tend to show up in there a lot.
Nice is a common rock for gravel.
Yeah. Yep. So
Confirmed from all the gravel I've had to move.
there you go. So texture. So that's not very nice, is it?
No, they're
Yeah, it's
Yeah, you guys have done a lot of gardening and stuff because your mom's kind of
gardening,
nutty about the gardening and shit.
building.
It's your dad? He's the one that does the gardening? Yeah, Jack's mom has a house plant affinity and
My dad's the one that wants to build the walls.
Ah.
My mom wanted to make all the walls turn into the garden.
And
there you
the
go.
one that actually makes the walls.
I just kill things that I plant. I try not to. You'd think I would be good at it, but I'm not. So igneous rocks, texture. All right, this is important to kind of understand with relationship to grain size. All right, so the texture of igneous rocks is dependent on the cooling rate of the melting magma. So if you have a coarse grained rock like this igneous up here at the top, that means that the minerals that make up the grains within the rock had more time to cool. Okay, so you can link all this together in your head if you keep focused for this little segment here, it'll make sense. So you've got these big grains And that's because the minerals, the individual minerals have more time to cool. Okay, keep that in your mind. And then you have the fine grain ones, and it had pretty fast cooling. And then you have like obsidian where it's glassy. That means it cooled really fast and the crystals did not have time to form. Now it seems counterintuitive because you look at it and you're like, that's one giant crystal, but it's not really when you're talking about mineral crystals. So they did not have time to form individual crystals. It cooled really fast. You get something like obsidian. So sedimentary rocks, keep that first stuff in your mind. So sedimentary rocks, their texture is produced by several things. It's the relationship between the mineral grains. It has to do with weathering too. So your grain size, that's determined by the mode of weathering. And like if you remember that that conglomerate, that was this one here, that was the clastic sedimentary rock. You can tell that these rocks or the rock portions that make up the conglomerate have been weathered more than these in the breccia, right? Weathering is, and we'll talk about this more next week, but weathering is the breakdown of a rock into sediment, okay? So then you have your moderately rounded ones. Those are sharp and angular. And then you've got your, and then you got your poorly rounded ones like in breccia, and they haven't been weathered much. That's affecting their grain shape. And then with grain pattern. So these are, you can consider them either poorly sorted, they say, or you can consider them well sorted or moderately well sorted. And basically that has to do with particles of similar grain size. And you can see this when we look at next week, when we look at like walls of sedimentary rock, you can see like what it means by sorted is, say you have an event that causes all of this rock to come into one area, and then you get build up over time. So you get the pressure and the heat that makes it metamorphic. You could see if it all landed at one time, that could be well sorted, meaning the larger grains are at the bottom because gravity would have pulled them down. And then you have kind of medium and then the smaller, and that's what they mean by well sorted. So your metamorphic rocks, your textures are going to fall into two groups, like we said. Now, this is another term, foliated and non-foliated. This is similar to banding. So foliated ones exhibit layers or stripes caused by elongation and alignment of minerals as it undergoes metamorphism. And some of these are also banded, but not all of them. And non-foliated are the ones that don't have minerals that align. So we'll look at it really next week, but what you'll see is, you'll see like chunks of minerals within a rock if you did a cross section. And let's say that the pressure and the way gravity was affecting it and the heat over time caused the rock to kind of go this direction as it was forming rather than straight down. You'll see the minerals in it get stretched and elongated. So you can see sort of like they've been pulled out, almost like putty, and you can really see the shape. It's pretty cool. So we've got what? Color, grain size, texture. All right, so another way, we'll get to another way in a minute. So if you look here, you've got a couple different ways that magma acts. These guys, they call shelves, and they're really cool. And then you've got over here, there's a pluton. So you see there, it looks like a fault line maybe. There's magma coming up, or at least heat. You got a volcano.
Cone volcano, it looks like.
Yep, there's lots of different kinds. We'll get to those too this year. So here's a little game we're gonna play. Yay! Okay, so we're talking about rock formation. So rocks usually melt somewhere between 800 and 1200. This is when they cool, sorry, between 800 and 1200 Celsius. So that's when they cool. So we can categorize rocks based on their silica content. Okay, silica. So silica is really common. Almost all rocks have some silica. And because of that, because it's common amongst them, we can use it to categorize them, say how much they have or how little they have. So when we talk about basaltic rocks, they have roughly 52%, like 42 to 52. This is how they categorize them. And you can see like rhyolitic is more than 66%. So silica is one of the last things, or usually is the last thing to cool. If you had to solidify, if you had an opportunity for like a massive magma full of different minerals start cooling, and minerals find each other and cool off and start to solidify at various rates, the last one to cool is going to be the silica. Pure silica makes quartz. Like if you've seen the nice clear quartz, that's pure silica. So if we look here, we have a little chart. We've got basaltic, andesitic, and rhyolitic. If you've got your binder open, you can probably play along in this little game here, but we'll see how we do. So number one here, it wants to know which of these is going to fall into that little blank. So what we're doing is, this says rock form from rocks in the upper mantle. So where do andesitic rocks form? If basaltic is upper mantle, where's andesitic? Does anybody know? Okay, Alex.
I'm gonna guess from deep beneath continental crust.
So that is
No,
right.
sorry, oceanic crust.
This one here,
Yes.
the one that says, wait a minute, not that one. And that says sediments. You don't want that one.
No, that,
Where is it? Sorry, this one. This one,
no, I meant oceanic crust.
oceanic crust. This one here.
Yeah.
That one says, and sediment. You sure you want to go for it? All right, let's see. Where does it go? Boom, you are correct. There you go. All right, so
Oh, that is off center.
yeah, it is, and it shouldn't be. I spent forever trying to fix them. So how about this next one here? What about rhyolitic? Where's that gonna form? Okay, Liam.
Deep beneath continental.
Deep beneath continental crust. Let's see. All right, very good. Okay, who wants to give me, this is how I'm checking that you've done your binder work. So if you haven't answered, you might want to answer. How about number 3? Do we know what's going here? You have a chart somewhere in your binder. Do you want to guess what it is, Piper? I meant to leave one of those blanks so you could really tell. I guess I filled them all up. So let's look here. You can see that this one is about viscosity of magma, and this one is about how they erupt. So this is going to be what type of silica, how much silica. So Jack, you want to give us number 3?
That would be low silica.
So basaltic, low silica says. Boom, good job. All right, how about this next one? This is andesitic, how much silica? Bailey?
About 60%.
About 60%. Oh, why are these all off center? I know. I don't know what happened. That row must have gotten scooched somehow. So how about this last one? This is an easy one. I wanted to give away. Oh, okay, Parker.
The last one.
The last one, which is going to be what?
Uh,
Silica. Which of these is? Okay, there you go. Good deal. All right, so then we come over to this category. So this is about viscosity. What is viscosity? Drew.
Viscosity is kind of like texture based on like how thick the liquid is.
Yeah, viscosity is actually about pouring, about how things pour. So if I had a slope and I poured water down it, it would have very low viscosity, which is run right off the slope. If I put syrup on it,
Honey.
it would go slower. Honey would go even slower, and molasses would be really slow. So molasses is the most viscous, right? So viscosity is about thickness when it comes to pouring. So who can do number 6? Let's see. Anybody who hasn't gone yet? Anybody? Chloe, you can do it. Can't you do it? Okay, so we have low viscosity and intermediate viscosity, sorry. And rhyolitic is going to be high. So what's going in the top? Yeah, low viscosity. You got it. Yep, easy peasy. Lily, you can do number 7.
What?
We got, Lily, we got intermediate viscosity. And then we have these ones about eruptions. Where's this going to go?
7.
Yep, intermediate viscosity is going to 7. You got it. Okay, good. Keep your ears open back there. All right, how about this next one? Eruptions. Who hasn't gone yet? Milo, have you got one yet?
No.
What do you think?
There's supposed to be a chart here, right?
A what?
A chart.
A chart? There might be one, or there's something similar, but if you just look, I think you can probably figure this out.
Not a chart in the binder.
Oh, there's not. Oh, I thought there was a similar one.
Think about.
Yeah, it's a similar one maybe, but it's not exactly the same. Okay, so where do you think we're going here, Milo? So we have basaltic is going to be, this is what you need to look at to figure it out. Viscosity. It's low viscosity, which means it's very runny. So do you think its eruptions are going to be quiet flowing, or do you think they're going to be explosive, most dangerous? What would you think? Yeah, because it's nice and thin. It's a thin lava that comes out. So yeah, All right, and then
I don't know what the last one could be.
you can do the last one. What's it gonna be, Scott?
I can't read.
Explosive eruptions. There you go. All right. I made everybody talk at some point. Still getting to you. All right, so this one's a quick video where this Australian lady, these Australian ladies have great science videos. Yeah.
I watched this video too.
Did you? This is a really good one. So this is going to help you see how everything is categorized in multiple different ways. I'm going to grab a drink while it plays, but y'all be sure that you pay attention. Don't chitty chat. Okay, because this is a good one. It's very helpful. Oh, spoon feed me. A little
Hi
spoon.
guys, the objective of this video is
She's
to
teaching
just
another
summarize
class,
all of
so.
the information we've covered in the videos just prior to this one on igneous rocks. So just for a really quick summary, we can see that we have ultramafic, mafic, intermediate and felsic rock. And we can distinguish between these according to how light or dark the rock is. And this coloration depends on how much of certain minerals is contained within the rock. For example, granite has a pink color because of the feldspar contained within the rock, while gabbro has quite a dark color because there is mineral quartz within the rock. We can then also categorize the rock into whether it is intrusive or extrusive. Intrusive rock showing crystal structure, while extrusive rock shows minimal crystal structure because it is cooled so quickly. So we know that the rhyolite and granite have very similar chemical composition, and we've gone over this in the past. And we know that the dacite and granodiorite have a similar chemical composition, same with the andesite and diorite and the basalt and gabbro.
Basalt.
They
She said.
because they're
Well,
all
that's really-
solidified in different environments. These are the main types of igneous rock that we need to know. And they all sit on this continuum according to how much silicon is in the rock. Here is a really quick flowchart just to see how we classify igneous rock. Firstly, we should ask ourselves, is the rock crystalline? If it's not crystalline and majority of the grains are fine with some small crystals, we say that it is extrusive. If it is a crystalline rock with a lot of coarse grains that are all interlocking, we say that it is intrusive. Once we've decided whether the rock is intrusive or extrusive, we then have a look at the color of the rock. If an extrusive rock is quite light in color, we would call it a felsic rock, and therefore it is probably white. If this extrusive rock is white with only some black spots, we would call it dacite. If we have a rock that is black or grey in color with only some white spots, it would be andesite. And a very dark rock would be called mafic or basalt. Any intrusive rock that is quite light in color and has some pink included in it is a felsic rock and is probably granite. An intrusive rock that is white with some black spots is granodiorite. When we have a black rock with some white spots, we call this diorite. And a rock that is intrusive, all black, is probably mafic, and therefore gabbro. And then we have a few terms to describe some special extrusive igneous rock. First, we have vesicular rock, which includes rocks like pumice and scoria. These form because of a release of volatiles when the magma hits the Earth's surface. Then we have glassy rocks. These glassy rocks can either have a glassy finish to them, or they can be vesicular. These form because of a very rapid cooling of the molten rock, and this produces an atomic structure similar to that of glass. Finally, we have fragmented igneous rocks, which form because of explosive eruption. These fragmented rocks include volcanic breccia and tuff, and they are formed of broken up pieces of exploded rock, volcanic ash, and lava. So now we should understand all the different types of volcanic rock and how to name them. The rock names I've used in this summary video are all the main types of rocks you will face in your course.
So her course is not my course, but still, that's the same idea, all right? So she does a really good job of kind of categorizing everything. Now, she talked about intrusive versus extrusive. Okay, so we hadn't quite gotten to that in here, but what's an intrusive rock, James? under the surface of the Earth's crust. And an extrusive rock is, Caitlin, you're looking at it. What is it?
Magma that crystallizes on the earth.
Yeah, on or above, yeah, at the surface or above the surface. Those are intrusive and extrusive. So,
Once it's on the surface, it becomes lava, so technically
Mhm.
extrusive rocks are never formed from magma.
technically, yeah, I guess, well, there's a point where it's like right at the line of crust, you know what I mean? Right at it. I'm not sure how that would go technically. I'm sure somebody spent 50 years of their life trying to make that decision and get it published, but yeah. So
It is not lava or magma, it is.
right. So here's where things start coming together. So if you remember
Wow.
back here, we talked about, let's take a bit. Hey, you remember back here, we talked about grain size, and we talked about how slow cooling produces these larger grains, right? Fast cooling produces no visible grains. Okay, keep that in your head. Woo! Okay, temperature. So temperature is going to, as depth is going to increase, as you get deeper into the earth, what happens to the temperature, Drew? Yeah, so do you guys remember? I'll come back to it. So yes, it's going to increase. All right. And then you have pressure. As depth increases, what's going to happen to the pressure?
Oh, I think you just talked about pressure.
Oh, no, but you can figure that out. As the depth increases, as they get deeper in the earth, what's going to happen to the pressure on the rock?
It's gonna get higher.
Yeah, it's going to increase. That's perfect. Yeah. So as the pressure increases, the temperature increases. Sorry, as the depth increases, the pressure increases and the temperature increases. And then we have melting point. All right. What were you going to say, Jack? You going to do it? Yeah, as depth increases, the melting point increases. All right. So now think about all these things. Okay. Think back to the larger grains, slow cooling. When we talk here about melting point, well, let me go back to this one. Melting is what? Drew.
When the molecules inside of an object spread apart,
But what happens, like states of matter, what is it?
when it goes from a solid to a liquid.
Right, so rock melts, right? Rock also freezes. So if you're looking here where it's really, really deep, okay, you're gonna keep in mind here that the minerals that have the lowest, the highest melting point and, well, the highest freezing point, I'm sorry, the minerals that have the highest freezing point, you're going to find them down in here because it's going to take them a while. It's got to be really, really, really cool for them to freeze. The freezing point is higher, right? So this is where you're going to find your larger grain stuff. So this is where you're going to find your silica. It's also more viscous, if you remember. And if you've got something more viscous, it's more dense. So it's going down. So keep that kind of in your head. So another thing that is going to affect melting point, just to keep in mind, is water content. So as water content increases, what's going to happen to melting point, Liam?
It's gonna decrease.
It's going to decrease. Okay, so you've got more water and your melting point decreases. So you have to think of it this way. It's going to melt at a lower temperature if it has water in it, more water in it. The more water, the lower the temperature needs to be before it starts to melt. So basalt, where is basalt going to melt? At a high temp, at a low temp? What do we think? Now remember, basalt, how much silica does basalt have? A lot or a little?
Well,
Well, now, oh yeah, he knows percentages. A little. Okay, it has a little silica. So is it going to melt at a high or a low temp, Bailey? High temp. Okay, at a high temp. Very good. So that means it doesn't need to get as hot. You have to think about it as a scale, right? So if you had 0 to 100, it's going to be obviously way different than that. But it's going to melt at a high temp. How about granite? Where's that going to melt, Piper?
Low.
At a lower temp. And then rocks with high what and what? What to, do we know what, these are elements. Do we know what we're dealing with here? that are gonna make them melt at really high temperatures? Drew, do you know?
Radioactive elements?
It's a good guess. Not that one though.
They do?
Yeah, they do. But there's something else that's really high. Do you know what? You know, Alex, what is it?
I think it's iron and magnesium.
Iron and magnesium. Wow, you got good. You're really good there at thinking of what it is. Iron and magnesium. These are the ones that are gonna melt at a really, really high temp, okay? So,
Tungsten?
tungsten, I don't know, tungsten's melt.
The tungsten's got a pretty high melting
Oh.
point.
Alexa, what's the melting point of tungsten?
Tungsten's melting point is 6,191.6 degrees Fahrenheit.
It's a little hot. All right, so partial melting. Now this is when you have different components in a rock and they melt, and then you have this magma that has these different components melting at different rates. So it's like slushy magma. You can think of it like a slushy magma.
Drink it.
So here's where it all comes together. All the things we've been talking about with high melting temperature, high silica, you know, where it is within the crust. Is it deeper or closer to the surface? This kind of puts it all together. Bowen's reaction series. So there's a video on this too, and you get to see a picture of Bowen. So I didn't have to put him in here. He's a Canadian dude. So he's really nice. So anyway, as magma cools, minerals form predictable patterns. This is what Bowen went off of. So he noticed that you had these gradual continuous changes. And he made this chart and he put feldspar on the right-hand side, and then he put abrupt changes on this left-hand side. And you'll see it when you really look at it. So calcium, as it gets hotter and it gets more pressure on it, it actually is going to change to sodium. And that is because the physical changes on the particular element are so strong that they end up causing a chemical change, which means you've actually got like the atoms within that particular element and the way they're arranged when they hold together is changing, and it's causing a reconstruction. So as crystals react to magma, if it's too rapid, what does it create? Do you know what happens if it's too rapid?
An explosion.
Not an explosion. It creates what we call a zoned crystal. Now, a zoned crystal, you can definitely find some on my counter. I've found them there myself. So a zoned crystal is when you have a rock and then there's like a crystal in it that's like big. It's a chunk of crystal. Okay, that's a zoned crystal, and it's in one spot. So that means you had rapid cooling of the rock, and then that's that stuff, you know, that makes the crystal either cooled first or cooled last. So then you have these abrupt changes. These are the iron-rich rocks. So cooling magma forms minerals in a specific order. Do you know what order they're formed in? Anybody know? So your first one is olivine, pyroxene. What you got?
Amphibole and biotype mica.
Amphibole and biotype mica. Very good. So they always do this. When magma's cooling, the minerals always form in this order. So you get this funky little chart that I had up during lab. It's really convenient because you can look at it and you can see it takes all of that stuff that we had before. We have all these different ways to classify, and it kind of allows them to be intersectional so that you don't just have like, there's this section and there's this section. It blends them together. So another thing to consider though, before we really look at that, is what we call fractional crystallization. So this is just know what it is. I'm not gonna this isn't gonna be on your test, but this is when you've got things that are cooling in the reverse order of the partial melting. So you've basically got just slushy stuff going on, right? And you've got crystals that don't react with magma. So then you get, you get minerals that are crystallizing kind of at different rates. And then you end up with feldspar and quartz last. Now this is the one to remember. Silica is the most viscous. It cools last. And it tends to be, if you had magma where, you know, you've got various densities amongst the magma, where do you think you're going to find the silica? At the top or the bottom? What do you think, Piper?
The bottom.
Yeah, because it's the most viscous, it's dense, it takes way longer to cool. This is why there's so much quartz that you find in chunks, like you find it little chunks of quartz in rocks, or you can find full quartz rocks. So minerals with the highest what are gonna form first? What do you think? What do you think I could want here? Alex, what you got?
Calcium,
Good guess. Yeah, we're talking about freezing points. So that was a good guess, though. It could have been anything. So minerals with the highest.
except, silica.
Yeah, okay, so, so this is where it gets kind of funky and hard to follow. In general, minerals with your highest freezing point are gonna form first. Here's why. Imagine your thermometer, top to bottom, okay? Your highest freezing points, usually when you start talking about highest, you start thinking like the most, and your brain kind of goes to the most cold because it's highest, but it's really not. Your highest freezing points is warmer, right? Because it's on your
Higher
thermometer.
temperature.
Yeah, your higher temperatures are your highest freezing points. So those, your highest freezing points, okay, which is where things are going to come together. So it's warmer, okay? So the things that freeze or solidify first are the ones that do it, when it's cooler. It gets really confusing because you start thinking high and low and whatever. But when you see the chart, it goes, oh. So as magma changes, new minerals form, which is what we were talking about. And minerals tend to settle out to the bottom or stick to the ceiling and sides of magma chambers. The earliest crystals that form tend to be what? Do we know? What?
Big.
The largest, right? And why is it? Because they have
The most time.
most time to grow. So they
Easy
start
to
forming and they have a lot of time to grow. Okay, so sometimes the center of a crystal has a different composition from the outside because the magma's composition changes. This is Bowen's reaction series. Okay, so I had this slide up during lab. This is really convenient when you look at it. So think about this for a minute. So we put our rocks into these categories he calls, come back. Okay, they call them ultramafic, mafic, intermediate, and felsic. Here's felsic. Okay, look down here at felsic. So this is your lower temperature, and this is your higher temperature. The first silicate minerals to crystallize are here, and you get pyroxene and amphibole and biotite and quartz. And when you put it all together, it makes good. Come on, where's my video? Hello, what happened there? Oh, okay, don't be like that. Play the video, silly thing. All right, so this is Bowen's reaction series, and it'll help clarify all of it, hopefully, because it gets a little, right?
If igneous rocks form magma, you may wonder, why are there different types of igneous rocks? Why are some igneous rocks dark colored, like gabbro, and others are light colored, like granite? In the early 1900s, a Canadian geologist named Norman L. Bowen designed a laboratory experiment where he cooled molten rock, magma, and monitored how the mineral composition of the solidifying igneous rock changed through a range of temperatures. What he observed was a repeatable, predictable sequence of silicate mineral crystallization that we now know as Bowen's reaction series. As he cooled the magma and crystals began to form, Bowen noticed that new minerals formed because the arrangement of atoms in the minerals changed, and so did the elements that made up those minerals. Bowen called this sequence of mineral formation from olivine to biotite the discontinuous branch, because during each step, a new mineral formed. In picture what happens when crystals form in the minerals, let's zoom in on a point of magma similar to what Bowen observed in his experiment. Notice that there are a variety of elements and ions within the melt. As temperatures cool and crystals form from the melt, they remove certain elements. The first mineral to form from the melt is olivine. Olivine is a very simple mineral to form. It contains iron, magnesium, and silica ions, which are isolated from each other. In other words, no oxygen atoms are shared between neighboring silica tetrahedra. Because olivine is rich in iron and magnesium, as it crystallizes, the melt becomes depleted in iron and magnesium. As the temperature of the melt continues to decrease, a group of minerals named pyroxenes form. Pyroxenes and olivine contain similar elements, but the atomic arrangement of those elements is slightly different, which is why pyroxene minerals look very different from olivine crystals. The silica ions within pyroxenes link up into single chains, which means that each silica tetrahedron shares 2 oxygen atoms with neighboring tetrahedra. Both pyroxenes and olivine are iron and magnesium-rich silicate minerals.
Sound.
The music's a vibe.
So now that both are formed, the melt
Yeah.
has a lot less iron and magnesium in it. That means, as temperatures continue to decrease, the minerals that form can only be made using the elements left over in the melt. Amphibole minerals form next, at cooler temperatures. Amphibole minerals contain sodium, calcium, iron, magnesium, and silica. So as these minerals form, the melt is now becoming depleted in those elements. Amphibole minerals have silica ions linked together in double chains. Finally, with continued cooling, biotite forms using the elements left in the melt. Biotite contains potassium, aluminum, and silica, and can incorporate any leftover iron or magnesium. Is what geologists call a sheet silicate. 3 oxygen atoms within each silica tetrahedron are paired with neighboring tetrahedra to create a sheet. The minerals that form first at the highest temperatures of Bowen's discontinuous branch are iron and magnesium rich, what geologists call mafic minerals. As temperatures decrease, less and less iron and magnesium are available in the melt to make minerals like amphiboles and biotite. Instead, elements like aluminum, sodium, and potassium are available in the melt to make what geologists call intermediate minerals. While mafic and intermediate minerals form in the discontinuous branch, another mineral, plagioclase feldspar, forms as well in what is known as the continuous branch. Similar to the discontinuous branch, as temperatures cool, plagioclase changes its elemental composition in a solid solution series that incorporates more calcium into its crystal structure at high temperatures, making a dark gray version of the mineral, and more sodium at lower temperatures, making a white version of the mineral. However, unlike the discontinuous series, the arrangement of the atoms in plagioclase does not change as temperatures cool. Therefore, because the atomic arrangement remains the same, the mineral is still plagioclase, just with a slightly different composition in what Bowen called the continuous branch of the reaction series. At cooler temperatures, the discontinuous branch and the continuous branch merge, and the minerals that form become more felsic. That means that they have less iron and magnesium in them, and more lighter elements such as aluminum and potassium. The formation of muscovite and potassium feldspar uses up most of the remaining aluminum, sodium, and potassium from the melt. By the time quartz forms, there is almost nothing left in the melt except for silicon and oxygen, which, when combined, form the mineral quartz silicon dioxide. Felsic minerals like quartz and potassium feldspar have all 4 oxygen atoms in each silica tetrahedron, shared with neighboring tetrahedra. Quartz is the final mineral to form in Bowen's reaction series. Because it forms at the lowest temperature and has all of its tetrahedra covalently bonded to neighboring tetrahedra, quartz is extremely stable at Earth's surface temperatures and extremely resistant to weather. That's why beach sand, which has sometimes traveled hundreds to thousands of kilometers from its source, is most often made up of quartz grains.
The more you know.
Yeah, so as you can see, it is super complicated, but
At Earth's
if
surface
it will let me go
temperatures
back.
and extremely resistant to weather.
What I want you guys to know is basically this bit here, okay? That I want you to be able to identify if a rock is, where a rock is on this particular scale. So if I put a picture of a rock on your test and it's light colored and I ask you if the rock is ultramafic, mafic, intermediate, or felsic, I want you to be able to know that. Or if I tell you that a rock, I give you a picture of a rock and it has large grain, you need to be able to tell me, did those grains did the minerals that make up the rock cool slowly or cool quickly? What would the answer to that be? Slowly, right? Okay, that's the kind of stuff I want you to know. When you get into all of this minerals changing chemical compounds, it gets really, really complicated, like super duper complicated. And I don't expect you guys to know all of that. I expect you to know certain things are going to be present everywhere, or almost everywhere. Like you're going to find silica in most rocks, and that you can use silica to categorize rocks. You can use color, you can use texture, you can use grain size, you can use all that stuff, right? That's what I want you guys to be able to understand. I don't want you to have to tell me this whole like continuum, because it's a lot. So whoop, I think I skipped one. Nope, I didn't. Okay, so we went over this a little bit ago, so you should know these. So where's somebody who hasn't answered a lot? Ooh, beneath the crust. I'm looking at you, Sky. We're talking about beneath the crust and above the crust. Do you remember either of those terms? For below, give me one. What's below? What forms beneath the crust? What kind of rock? Can't remember it. Let's see. Chloe, do you remember? Intrusive. You got it. Okay. So if it's intrusive that forms beneath the rock, then Sky, what's the one that forms above? Yeah, you got it. That a girl. All right. Good job. So extrusive. Okay. So you have your intrusive and your extrusive rocks. If you look right over here, there's some images for you. Okay, so you see this, there's a dike and a sill. Like I said, sometimes they call them a shelf. There's the sill, there's a dike here. That means it goes straight up and down. Sill goes across. And then you have a pluton down here and a batholith. Batholith. I love that.
Sounds like you have a list.
Batholith. Yeah, that's word sounds wrong. Batholith. So intrusive rocks, cooling time tends to be thousands of years, and your texture is going to be small, medium grains, and sometimes ones you can't even see. But your extrusive rocks, they can cool. Some that are really large is what I meant to say, that you can really, really see. And then your extrusive rocks are going to cool from seconds to months, and they are invisible or microscopic grains. So somebody then give me an example of an intrusive rock. One of the ones we talked about. Bailey?
Quartz.
Quartz is intrusive. Good. What's another one? Drew?
What is that? Is it rock and nickel?
That's a
Metal.
that's a metal. What's a rock or a mineral? What's a mineral that you might find in a rock that's intrusive? So it's going to form underground. Can you think of that? What it might be? He's thinking he doesn't know. James? Okay, there we go. All right, so what's going to be, what now?
Basalt.
Basalt. Okay, so what's going to be an extrusive rock? Ooh, lots of them. All right, Caitlin. Obsidian is a great example.
It went out.
That's all right. I don't touch those figures, are not mine. That's an extrusive rock. That's your like classic extrusive rock with no visible grain. All right, James, what's another one? Granite's intrusive. Was an extrusive. I have another extrusive one. Lily. That's intrusive. Underground. Drew?
Sandstone.
Sandstone is sedimentary, so it's above ground, but I should clarify. What's an igneous rock that's extrusive above ground? Liam?
Rhyolite?
Rhyolite?
Isn't the
No.
type of
Yeah.
fine grain?
Yeah. It's closer. Yeah.
Limestone.
Limestone is going to be more sedimentary. Okay. So the other one I'm thinking of, your other classic. Do you know what the other classic one is? Do you know?
Amethyst.
No, it's inside.
I was gonna say pumice, but
That's it. Jack
Yes.
got it. Pumice.
That's
Okay.
why I was-
So
That's what I was going to say.
you're
Jack.
too big. Think about it. Extrusive rocks that form on the surface. They look super different, right? You've got where's this? There he is. So you've got pumice and obsidian. All right. Pumice and obsidian. Where is my pumice? I'm gonna go by number because I'm not crazy. There's not obviously in there. And then the other box. I've got so many boxes of rocks. Box of rocks. Here it is, 8 and 9, this box. 7, 8, and 9, okay. Pumice and obsidian. Completely different. Which one is the obsidian? Just point at it. Yeah, so this one's the pumice, all right. The difference between these is,
One's used on your feet, one's used to kill people.
so this one cooled, yeah, it is actually, they made this into arrowheads and whatnot, right? This cooled really quickly. And it's glassy. But what do you think made this one? This one's almost like it's like a rough sponge. What do you think made this one different? James, what do you think? Gas bubbles. Now, what might have caused gas bubbles? Can you think of some things that might have caused it? What are some things that cause gas? Let's see. What you got, Liam? You got one? No, who has, Drew?
Bubbles, of hot air forming inside magma.
Right, but how's that happen? What might cause gas inside of the magma? Can you think of anything? Jack, what do you think?
I mean, energy, heat, maybe.
Maybe, Bailey.
Water evaporated.
Water evaporating. Okay, water gets so hot, it's water vapor, and it's gonna be water vapor anyway if it's inside magma, right? But the hotter it gets, that water's still there, but it's gonna expand, right? And it's gonna get bigger and bigger, and then you get this. Or if there's water on the surface that it's coming in contact with, or water in the air, a lot of water in the air. What were you gonna say, Jack? I mean, Alex, sorry. I looked at Jack's name when I said it.
Also, pumice is normally formed from volcanic ash, which normally has air mixed in.
There you go. So
And
air
another
mixed
way
in.
to create gas is having too much Taco Bell.
There's that. So, yes, so hummus, you got a lot of gas in it because it's mixed up, right? It's not pure lava. It's got ash mixed in with it, so it's got other gas in it. Another way you can get gas formation is a chemical reaction, right? So it can be something expanding or chemical reaction. I'll pass these two around. Don't scratch up my pumice too much because it, you can break it off, it comes apart. But this they use for sanding. Like I said, you can get pumice sticks and you can scrub your grout and your tile. If you get a pedicure, they rub it on your feet, right? Because it's really scrubby. Whereas this one, it's gonna chip off in nice little level planes and you can make arrowheads out of it, right? So
Stab people.
yes, you can. Put your glasses around so you guys can see like side by side the difference. So they're very different, even though they are both extrusive. All right, so let's have a look at these. So here is your Bowen's reaction series broken down a little bit more. So what is dark colored, low silica, plagioclase, and pyroxene are examples. So look at the chart there. Where would you find dark color, low silica? Chloe. All right, she's got ultramafic. Okay, so well, basaltic, that's what it wants. But yes, you're in the right area. So yes, all right. So what's Chloe's name? There it is. All right, so now you know you're looking for a basaltic. So so she answered up from this upper column. We're looking in this one. So what's light colored high silica where you're going to find quartz and feldspar? Yay, he's going to break his shoulder. Caitlin.
Ultramafic.
Granite. So we're looking down here in these. But yeah, you guys are on the right track. Throwing things. I keep throwing things today. So this one actually is a little, that's messed up. It's in between. You can see intermediate there. So if I have basaltic, granite, intermediate, do you know what the other one is? James? Felsic, yeah, and ultra basic, but yeah, if you were looking at these, you could do felsic, but ultra, should say ultra. Is that wrong?
If you smelled it.
I mean, it's ultra basic, but it's also called.
Yeah, ultramafic. I think it auto-corrected me.
No, it's called
Smells a bit like
Yeah,
preservation chemicals from last year.
ignore that, I'll fix it. So, if you find a rock with coarse grains, how did it cool? Piper. A rock with coarse grains, how did those minerals cool? Slowly or quickly? Yeah, slowly, because they had time to form big crystals. slip crystals. If it's fine grain, how did it cool, Chloe? Quickly, yeah, all right. And then if it is glassy, how did it cool, Liam?
Very quickly.
Very quickly, you got it. All right, now. Porphyritic is well-defined large crystals with fine crystals and a complex cooling history. So that's what you find here. This is when you get a rock that's like all screwed up. And then what's vesicular? Liam,
Dissolved gases.
there you go.
Like pumice.
Drew, you got a vesicular rock in your hand?
Yes.
Which one is it? That one right there. Pumice is a vesicular rock. Oh, it's the queen. Oh, sorry. There's European money in here.
Oh,
It's
really?
1 pence and it's got Elizabeth on it. Bye, Elizabeth.
I need it.
You all know to watch the funeral, right? It's the 19th, so it's Monday, I think. Yeah. Like it's gonna be amazing. So
Did
yes.
Alex eat it?
No. Yeah, I mean, you guys actually might get to see this twice in your life. Hey, and I probably will too, hopefully, because Charles is pretty old. So, but still, there are very few people on the planet right now who've seen the funeral for a British monarch, if you think about it, because it happened when she was 25. So that's a long time ago because she's 90. What was she, 93? 96? Yeah. Yeah. So
She won the 19 this year.
anyway, it's worth watching. It's gonna be really cool. I got to see and live through the big royal wedding with Charles and Diana when that was a thing. And then Diana's funeral, which was incredible. So I watched for the music, but it's gonna be interesting
It's
nonetheless.
wild that
Yeah.
a person for 96 years has rule over a country.
Well, since she
not
was like 25, but what's even crazier when you think about it is, do you know that she wasn't in line for the throne when she was little? Like her father was brother to the monarch. And do you know why Edward, her father's George VI, right? Edward was her uncle. He was king. Do you know why he was no longer king and her dad had to take over? Does anybody know? It's interesting. Do you know, Chloe? He did step down. He abdicated, but do you know why? It's crazy. Do you know what?
He stepped down so he could marry a non-royal
Yeah, do you
from America.
Yeah, not only was she not royal and from America, she was divorced, and that was the problem. She was divorced and they can't have that. So he wanted this American divorcee so much that he abdicated the throne, which meant his brother took over, which meant Elizabeth was in line. Kind of fascinating weirdness, right? Very interesting to think about it. You don't,
I really hope it worked out for him otherwise.
I mean, yeah, gosh, it's given up a lot because it was one of those things like, if you go, you are gone, like no more, any of us.
No mas.
Goodbye. So he was very gone. Yep. So igneous rocks as resources. Okay, there's lots of ways we use rocks as resources. So what often contain valuable ores? Do you know where we find them in what, Chloe? In veins. She's got it. So, you know, that one is, that's easy. That's gold, right? That's
Or pyrite.
or pyrite, but it says valuable. So I'm thinking it's not pyrite. So there's gold there.
Like fish can be valuable.
In vein, right? And you can typically find a lot of these ores for precious metals and whatnot. I'll take these, James. You can find them where you find quartz veins. So like if you go to the mine in Dahlonega and you go down inside the mine, there are these massive like hollowed out quartz veins where they pulled the gold out. It's pretty neat.
And I lick the walls.
What's with you and licking? Are you just like really orally fixated? It's kind of odd.
I'm not thinking
Yeah. So what do you call,
Georgia.
see this is brilliant here. See big long chunks of it? See how it formed in the hexagonal shape, but it's in a big long column. Do you know what you call those? When they grow like that?
In columns.
No, the green thing? Do you know what you call them? Guys, but leave a hand alone. Do you know, Piper?
Like the type of mineral or?
What do you call that kind of structure? What grows like that? Do you know? Lily, do you know? We're getting there. So this is what you call a pegmatite. So that's what the big long thing is. You can think of it like a peg you stick in a board. Do you know what that is?
A wall.
Anybody know this? Anybody know what that is? Do you know, Liam? It's a kimberlite. So that means it's a diamond intrusion. So when you get a diamond intrusion in a rock like that, it's called a kimberlite. Now, you can get intrusions in diamonds when they take a diamond and they really look at it, try to figure out how valuable it is. They look for intrusions, like little tiny minerals, a little mineral crystal formed in there. I mean, you get the little tiny microscopic ones because they get real picky. All right, so that's a diamond intrusion. That's a kimberlite. And then lastly, strength and durability example would be granite. What we're looking for here is construction is another way to use that. Now, diamonds. Does anybody know what the main controversy over diamonds is? Nobody cares about my calendar. Do you know? Anybody know? Anybody? Look, come back to her in a minute. Go away. Go away. I don't want you. Why are you here? Oh, keep going. Anyway, it'll go away in a second, I think. Anybody know what do you know, Lily?
Stupid answer, feather blue.
No, that's not it, but it's a good try. There's actually a big like a social and political controversy over diamonds.
The cost of the.
Well, yeah, there's always going to be a controversy over the cost.
Yeah.
Do you know, Bailey?
That they actually aren't worth that much. Someone just bought them up and stated their price.
It's a good guess.
Sounds like.
All right, what do you think,
sounds like
Alec?
what an American.
They weren't actually worth a whole lot until some smart person, I guess, in marketing for jewelry said to use them for wedding rings and the like because
That's true. That's true. So this is actually one of the things that got discussed in that podcast I was talking about, but diamonds are rare. So that does make them valuable and they are really durable. So if you wanted to wear an opal as your engagement stone and you wore it every day for however long you were married and you banged your hand into stuff and went about life, it would not survive. It's too soft. A diamond though, you can bang into just about anything. You can scrape it on stuff. You can whatever. It's not gonna scratch. It's mine. I mean, I've had mine on for 20 years and it's got no scratches, no dings, no nothing. It's in perfect shape. If you hit it just right, you can crack it. But typically they're so durable, they're gonna last. The second most durable would be sapphire. And you can get sapphire in different colors too. Tourmaline in particular, you can get in like, tourmaline has like 20 different colors. It's amazing how it comes in different colors. So that's part of the reason. But the biggest controversy over diamonds is whether or not they are, sometimes they call them blood diamonds and sometimes they call them conflict diamonds. So there's actually a really great movie called Blood Diamond, but it's kind of like a little gory in your face. It's got some really violent stuff. So if you're not into that, don't watch it. But anyway, diamond mines. Do you know where most of the world's diamond mines are found? What continent, you know? In Africa. Okay, so political situations in Africa can be kind of fraught, right? There are boundaries in Africa that were made by, a lot of them by, Queen Elizabeth's ancestors when they went in there and said, we'll take this, and we'll take that. And they put up boundaries, but those boundaries weren't necessarily like the natural boundaries for the tribal communities and whatnot that live there. So people got divided where they shouldn't be divided. And then like there were outsiders coming in and ruling and then leaving. So there's been a lot of political turmoil. So what happens with diamond mines is if a political force gets a hold of a diamond mine, they will use the funding from that to fund all of their actions, very often against their neighbors, right? So in those countries, some of them, if you want to get good, cheap labor in your diamond mine and you don't want to use your own people, you just go to the country next door that you don't like and you swipe their children and you throw them in the mine. And that happens. There are not just from another country, but maybe from your own too, but there are children in diamond mines. There are people that are treated really, really poorly in diamond mines. So there are people who don't want to buy what they call blood diamonds. Those are called blood diamonds because people die for the diamonds. They want to buy conflict-free diamonds. What percentage, I had it earlier, what percentage of diamonds that you're going to find every day are conflict-free? It's kind of low, actually. What percent of diamonds are conflict-free? There it is. The diamond industry estimates that conflict diamonds represent 4% of the total trade. Now that's the diamond industry, but if you look at it from people not in the diamond industry, they say it's much, much higher. So it's not uncommon that, somebody is wearing what you call a conflict diamond. Drew.
I was gonna say that same kind of stuff happens with, in China with iPhone, Apple.
Oh, yeah, it does sometimes. Yeah, some of the particular factories, yeah,
If you're going to employ labor,
Mhm.
it doesn't make sense to use children who are normally weak and fragile.
Well, they would pick, you're a little tall, but they would snag, when they do this in those kinds of countries, and it's not just for diamonds, they turn them into soldiers and stuff too in some places, right? They'll go in and steal children and make them into soldiers, and they'll do things like, horrible things, force them to do horrible things until they kind of break them. But they tend to pick, boys around 12, 13 are just about right for that. That's who they snag. So, and you don't need to be really strong to work in the diamond mine. You just need to swing a hammer all day, and you need to sort through rocks and move rocks around and all that. So yeah. So this lady does a really good review here of our big Pluton here. So what's Stone Mountain? How was Stone Mountain formed? We've all seen it.
All right, have you ever looked at Stone Mountain from a distance? It's like a big gigantic rock that's not just drop there.
It
Is
does.
that how it's formed? It'll be exciting. So how do you think Stone Mountain?
Those are.
No.
How do you think you did?
People give good answers here.
Got amazing power in order to explain.
How did it form?
God did it, he says.
How did God form the earth? He just like said it,
Came up from the ground, moved up.
Move up from the ground? How did that happen? That's a science question.
I love that answer.
That's a great one.
Yeah.
That's the science
We
question.
have here.
I want that man to be my friend.
That'll show you how Stone Mountain formed as magma first, deep underground. So molten rock, about 8 to 10 miles that would be underground. This cooled, and it was still underground, so we needed certain forces that would uncover.
It's long believed to have begun over 300 million years ago, as the mountains were formed on the earth, including in our area by land masses colliding together. Pockets of magma were trapped underneath, and the minerals in the liquid form of Pacific rock type, what we know as granite. So how did it get to the surface? Well, a couple of forces were at hand.
And that would be weathering. This is where rocks will really break down through different processes. And then erosion, which is going to move all of this sediment from on top of the mountain.
Stone Mountain is about 1,868 feet high and stretches out roughly 10 miles as far east as Centerville, Georgia. So far, about 10% of the mountain is above ground, making it the world's largest piece of exposed granite. It also means that 90% still remains below the surface. So one could assume the surrounding land is eroding at a faster rate than the mountain is.
Pretty cool being on top of it.
I think it'll look really much the same as we see it today, because we have the same forces that break it down, right? Weathering, erosion, we're always gonna have wind and rain. And maybe people who are doing a little bit of that breaking down as well.
Yeah, because it's slippery. Yeah, because it's got so many chunks sliding off. It's doing sheeting erosion. Now, this is a different stone mountain. Did you know North Carolina has a stone mountain? Aha, it does. And this guy talks about it like it is the best stone mountain. I'm sorry, I'm going to say ours is the best, but he does a good little report too on how this works. He's very excited about it, and this goofy lady with him.
That kid was very aggressive.
She goofy, this one.
That was a good.
Hey guys, I'm here at the North Carolina Museum of Natural Sciences here in Raleigh. We're gonna take a look at the rock samples from all over North Carolina.
She's
And I'm here to talk to.
really excited about
Senior geologist, Randy. Hey, Randy.
Hey, how's it going?
What's good, Randy? Being a geologist.
Well, I think rocks are really cool, but I really like the stories that they tell.
The stories that they tell, sounds like I need to listen a little bit closer to some rock.
How about you look a little bit closer?
Oh, second,
Keep
catch up.
rocking this.
See if I can get the thing to catch up. That's weird.
Definitely for me.
Yeah.
How the course of erosion.
Once he gets past the goofy girl interview, he does some really interesting stuff on the rock.
I think so. They're igneous, metamorphic, and sedentary.
She's thinking
right?
really hard about it.
And igneous, guys come from hot liquid rock or
That's
magma,
how you
right?
start a conversation right there.
This is how adults talk on the street.
Now, there aren't many places you can go and see molten magma in North Carolina today, but you can go to places where long ago, big pockets of magma cooled deep underground, and then after millions of years of erosion, you can now see that at the Earth's surface. And one of my
Yeah.
My eyes are cringing shut.
Is granodiorite pluton called stone mountain.
Yeah.
That's what I'm saying.
You're moving my head. You don't have to talk to her anymore.
Absolutely.
There it is.
Stone mountain is part of a much larger mass of rock that geologists call a pluton. This rock is similar to granite. It's called granodiorite. And we can tell that by the many different minerals that make it up. These include.
He's using a stick.
What feldspar?
Found this stick on the ground.
There might be another black mineral in here called amphibole.
Stick might be smaller than the finger.
These minerals are
Yeah.
crystallized. So you put hot magma deep underground. That magma cooled, crystals grew to the form of rock that we have here today. Now, since this rock formed from magma, it's called an igneous rock. But this rock didn't stay deep underground. Weathering and erosion has gradually uncovered. There's a special kind of weathering here that we call exfoliation.
See, that's why this is worth watching. See that? That exfoliation, that's what happens to Stone Mountain. Those sheets come off, right? You can see a good example there.
Also, roots and ice can grow into cracks and pop bits of rock off too. Now, once these pieces are broken, gravity, water, and wind all work to move them downhill. And if you look at the bottom of Stone Mountain, we can see all piles of broken rocks. Some of these pieces are kind of small, and some of them are really huge.
Huge.
Moderate size.
He's very excited about it. So these will be available to you when you look at your teacher ease, or if you want to go back and watch the videos, you can see your answers to these. Yep. And it is about time for you to head out. And since a lot of you have a lot of cranking to do over there on the machine, I will let you go and do that. So next week, we will meet again. It shall be fun. Lily, get your money, babe. She's leaving without the money.